And this is Tech Math 2. And we are currently in section 10-3. And Nate is complaining again about not being able to see properly. He doesn't have his glasses on or something. I don't know what it is. And so now the projector is projecting, so we can, is it okay to proceed now?
Yep.
Okay. It goes all the way to there and all the way to here, and you see what I'm saying? Okay. So everything's back to normal now. And we've always dealt with degrees. I could spell degree. So we have degrees, we have minutes, we have seconds, and there's 360 degrees in a circle, and there's 60 seconds in 1 degree, and there's 60 minutes in 1 second. And the Babylonians gave that to us prior, 200 years prior, 2,000 years prior to Christ's coming. So 4,000 years ago, the Babylonians gave us 360 degrees in a circle and 60 minutes and 60 seconds, and that was applied to our clock thing. And we had nothing to say about it. The French and the English couldn't change it. It was too far into our culture. And anyway, but the mathematicians decided that, you know, it'd be far easier to use something called radians. And so what I'm going to do is I'm going to take a circle. And so there's a circle, and the circle has a radius, and we all know that. Maybe we all know that, r. And if I take that radius and I were to wrap it around the outside of the circle, that same amount of r, that angle distance there would be called 1 radian. Okay, well, what's the circumference of a circle? Pi d, right? 2 pi r. Wait a minute, this r is the same as that r, right? So 2 pi is the same as going around the circle once. 2 pi. So 2 pi is the same as 360 degrees. So that's how we do that. So if I have pi radians, I have 180 degrees. If I have pi over 2 radians, I have 90 degrees. If I have pi over 3, I have 60 degrees. If I have pi over 4, I have 45 degrees. It doesn't look like 4s there, do it? Pi over 4. If I have, what's next? Pi over 5? No, pi over 6, 30 degrees. So those are the normal ones we use, pi, 2 pi, 3 pi, 4 pi, whatever. And then we go and we look at our circle again. So there's our circle again, and we put an XY plane in it. Oh, that was good. That's perfect there. Way to go. Now try it again. Is that better? XY. So now I go around the circle, and I'm at pi over 2, and I'm at pi, and I'm at 3 pi over 2, and I'm at 2 pi. And then I go and put a line in at 45 degrees. There and there. Well, that's perfect, yeah, 45 degrees. Okay, so now I'm at pi over 4. I'm at 3 pi over 4. I'm at 5 pi over 4. I'm at 7 pi over 4. And then I throw in another one right there, one over here, That was good. Was that good? One over there. One over here. That was really wonderful. So I have now 30 degrees between each of these guys. So that's the guy's 30, that guy's 30, this guy's 30. So now I've got pi over 6, and I've got pi over 3. And I got, what I got, 2 pi over 6. 2 pi over 6?
4 pi over 6.
4 pi over 6, sorry. 4 pi. Okay, so I got pi over 6, pi over 3, pi over 2. This is 5 pi over 6. 5, no, it's not. This is 5 pi over 6 over here. 5 pi over 6.
That's 2 pi
And
over 3.
this is 2 pi over 3. That's what it is. 4 pi over 6, really. And then I got 11 pi over 6, maybe?
Well,
No, that can't. It got to be 7 pi over 6. 7 pi over 6, and then over here I'd have 9 pi over 6. That'd be 3 pi over 2, right? 3 pi over 2. No, this is 3 pi over 2. So that can't be 3 pi over 2. So it's
4 pi over 3.
4 pi over 3. Really? 4 pi over 3. And this guy over here would be, this guy's the 11 pi over 6 guy. And then this guy should be probably 5 pi over 3. 5 pi over 3. All right. So I could do a circle like that and make all those things come up. So now the issue is, if I have degrees and I want to go to radians, what do I do? Well, on my last calculator, I could just change it. I had a convert thing, right? And on this calculator, I got a convert button. So the 8 guy is a convert button. And I come down and I can see I can go metric, and I can go temperature, and I can go speed, and I can go length, and I can go power, and I can't go degrees and radians. But if I put my calculator in radians, so I put my mode in radians, and I got 137 degrees, and I go 137 second function complex. No, that's not what I want. Second function, no second function, math. I just want math. And then I go to degrees, minutes, seconds, hit a 1 to get degrees. And now I got that this is, thank you very much, you stupid calculator, 137 over 180 pi. Yeah, obviously I've got it in the mode I'm in is math, whatever, math print. No, it's in classic. Oh well, can't have everything. But I could have 137 divided by 180 times pi. Okay, so I've got 2.3911 radians. All right. So what I do, if I don't want to mess around with my calculator for the rest of my natural life trying to make it work, is I say, well, pi radians is to 180 degrees as whatever my number is, 137 degrees, is to x radians. And then I do a cross multiply and solve for x. And that's how I would do that. Okay, on page 363, we come up with a table that I've given you before, but we'll do it again. And this is how I remember my sines and cosines and tangents. And we won't do them all, but we'll do some of them. So I got 0 pi over 6, also known as 30 degrees, pi over 4, also known as 45 degrees, pi over 3, also known as 60 degrees, and pi over 2, also known as 90 degrees. Okay, and we go and put down 0 over 2 and square root of 1. Square root of 0 over 2. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and the square root of 4 over 2. And that's how I remember my sine guys. And then I normally don't write that down. I normally put a 0 and a 1/2 and a square root of 3 over 2. And, well, that's square root of 2 over 2. And a square root of 3 over 2 and a 1. And then the sine guy goes the opposite way. And I wrote it up too high, so I have to write it down some. Cosine goes the opposite way. So cosine, the 1 goes first, the square root of 3 over 2 goes second, the square root of 2 over 2 stays in the middle because of the same 1/2 and 0. And then I do the tangent by saying tangent is sine over cosine. I could spell sine. And then I get what my tangent is. So that's how I remember it, and then I go back and get those guys up front. Okay, any questions? We also have to deal with reference angle, right? So we did reference angle in degrees last time. Now we're going to do reference angles in radian. So in the first quadrant, my reference angle is my reference angle. In the second quadrant, my angle is pi minus the reference angle. In the third quadrant, my angle is pi plus the reference angle. And in the fourth quadrant, my angle is 2 pi minus the reference angle. And that's the way I handle that if I want to think about it in radians, which of course I do because I'm one of those weird type of guys that want to think about that. Now, when we get to chapter probably 28, we see that the sine of x has a series approximation that's 1 minus x cubed over 3 factorial plus x to the 4th, x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and continuing on that plus minus, only having the odd powers of x. Now, if I were to put in there the sine of 90, sine of 90, and I know the sine of 90 is 1, right? Yeah. So I go in there and I go, okay, I'm going to go 1 minus 90 cubed divided by 3 factorial plus 90 raised to the 5th divided by 5 factorial minus 90 raised to the 7th divided by 7 factorial. And I hit the key and wow, I get 1, 2, 3. I get minus 9 times 10 to the 9th. Yeah, 10 to the 9th. That doesn't look like 1 to me, does it? But if I take the sine of pi over 2, and I go 1 minus the quantity pi over 2 raised to the 3rd power divided by 3 factorial plus quantity pi over 2 raised to the 5th power, wrong button, raised to, where's my raised to? Raised to the 5th power divided by 5 factorial minus quantity pi over 2 raised to the 7th power divided by 7 factorial. I end up with a wrong answer, 0.429, which is totally impossible if I would have put in the numbers right. Pi over 2, pi over 2. So I don't see what I'm doing wrong. But I obviously did something wrong because that should have came very close to 1. But the series approximation has to use radians in order to make it work. And from a number point of view, there's good reason for that. I just don't remember what it is now. But we'll worry about that when we get to chapter, if you ever get to chapter 28. Exactly. Okay. It was my Calculus 1 instructor, and he was the vice chairman of the math department at Michigan State. And he has 2 proofs that, and he's going to prove that sine and cosine exist. Now, only a real math person would care to prove that sine and cosine exist, right? But from first principles, sine and cosine exist. He has a short proof that is only 2 days long. The class is an hour a day, so it'll take about 2 hours. And then he has a longer proof that's 5 days long. And but the shorter proof is wrong because the shorter proof uses radians. And as soon as you use a radian, the assumption that you have radians also is the assumption that sine and cosine exist, so you can't use radians. So he commences the 5-day proof. And on the 4th day of the 5-day proof, he uses a radian. He throws his chalk down and walks out of the room. We don't see him until the next day. Anyway, I just, you have math majors and you have math majors. Okay, so that being the case, we're going to do problem number 1 first. 135 degrees, and we want to express it in terms of radians. Not only do we want to express it in terms of radians, but we want to keep the pi there too. Okay, so pi is to 180. Has some number of radians is to 135. All right, so r is equal to 135 over 180 pi. I'm just not doing well at all here. All right, and we normally, when we talk about radians, we normally leave pi in there just for the heck of it. We don't take it out. So 135 divided by 180 equals 3/4. Really? Yeah, it is. Yeah, 3/4. So 3 pi over 4. We normally wouldn't call it 3/4 pi. We would spell it 3 pi over 4. Oh, well, that was okay. Well, we'll do number 3 next. Anybody want to do number 3 for me? Number 3. 90 degrees is pi over 2 radians. And when we express it pi over 2, we don't have to put radians there because we know it's radians because it has a pi in it. But we could write radians there if we wanted to. Number 8. 8? Okay, that's good. 2,490 degrees. All right, so pi is to 180. As my answer is in radians is to 2,490. So we're going to cross multiply 2,490 divided by 180. Pi is equal to the number of radians that I've got. All right, well, the 0 goes away. 2, 4, 9 over 18 pi. I notice that I can divide top and bottom by 3, so I will. I divide top and bottom by 3, and I have a 6 there. 3 goes into 24, 83 times 83 over 6 radians. Really? You gotta be kidding me. Yeah, 83 over 6 radian. Oh well, can't have everything. So final answer, 83 pi over 6. All right, good enough. Change back to degrees. Okay, so I'll move on to 14. And I have 12 pi radians. Well, if 2 pi is 360, then 12 pi is going to be 6 times 360. All right, so that's going to be 0, 6, 3 to carry, 2,160. 6 times 360. Oh, lucky guess. And unlike radians, we have to put a degree guy there, so put a degree guy there. Okay, number 16. 1.82 radians. All right, well, pi is to 180 as 1.82 is to x. So x is goes over there. 180 times 1.82 divided by pi. And let's see if I can get my almost. All right, that's better. Time for the calculator. 180 times 1.82 divided by pi. 104.2783187. Yeah, it doesn't say how many significant digits I should keep. I think I'll keep 3. 104 degrees. All right. Now, well, we got find the reference angle. Okay, so we'll do 18. And we probably want to find the reference angles in radians. Okay, so we got pi, 6, 5, whatever it is. All right, 5, 6 over pi. So we notice that this is in the second quadrant, and we remember that in the second quadrant, the angle is equal to pi minus the reference angle. So the reference angle is pi minus 5 over 6 pi, also known as 1 over 6 pi. Pi over 6. All right, that'd be good. Pi over 6. Okay. 24. 24? No, 23. 23. Okay, so I've got minus 8 pi over 5. Minus 8 pi over 5. All right, so that looks like I'm over here. It looks like that's a third quadrant guy. Does that not look like, yeah, it looks sort of like a third quadrant guy, I think. No, he's not. It's not a third quadrant guy. It's a first quadrant guy. Is it a first quadrant guy? It's a first quadrant guy. Yeah, I think. So 10 pi over 5, also known as 2 pi, minus 8 pi over 5 gives us 2 pi over 5, which is less than a half. So that's a first quadrant answer. Yeah. Wow. Now we can go the other way. We can go and say, yeah, we're not going to do anything else other than that. All right. Use the table 10-4 and find the exact answer to this number. Okay, I guess we can do that. We'll do number 30. No, we won't. Yeah, we do. Number 30. Okay, I'm going to go back to 504. Okay, there we go. I'm on 10-4, and I want the cotangent of minus 5 pi over 4. Where the heck is that? Minus 5 pi over 4 would be over here, right? So the reference angle would be pi over 4, pi over 4, and the cotangent is negative in the second quadrant, so my answer is going to be minus square root of 2 over 2. No, it's not. Who wrote that down? Somebody wasn't paying attention. Minus 1. Better? All right, minus 1. Okay. Now, I could have just as well taken my calculator and gone to radian mode, right? Put the mode in radians. Okay, so my mode's in radians, and I'm going to find 1 divided by the tangent of minus 5 times pi divided by 4, and hit the dealy-dob thing. And why am I in degrees? Didn't I just put you in radians? I'm sure I did. All right, I'm going to try it again. 1 divided by, parentheses, the tangent.
1 over tangent.
Yeah, 1 over tangent. Tangent minus, and you can't use the negative, you have to use the negative key, not the minus sign. Not the subtract key. Minus 5 times pi divided by 4. Close parentheses. Boom. Minus 1. Calculate. Yeah. Yeah. Don't be using the subtract key. Use the minus key. What's wrong with you? Yeah.
Slightly longer.
Yeah. Slightly. You can tell. You can see the difference. It's clear right there. Yeah. Now, why did they do that? Why? Anyway, they did. That's all that matters. They did it to you. You're hosed. Okay, we'll do 30. We'll do 32 next. This way.
If we write minus negative like that.
Huh?
If we write minus and negative like that.
Yeah. It'll hold you over.
It'll look like an equal sign.
Yeah, it might. Yeah. Oh, I'm sorry. It looks sort of like an equal sign. All right. So there's the minus. There's the negative. All right. There you go. Now I got it. Must be true. Right in the paper, didn't you? All right. So we want to go 0 to 2 pi. And we want to find, this is 32. We have the sine of theta is square root of 3 over 2. And we're using the table on the other side, so I look over there on the other side, and I see square root of 3, table 10-4. Square root of 3 over 2 is pi over 3. Pi over 3. Am I done? Is that right?
Square root of what? 3 over 2.
Yeah, square root of 3 over 2. Oh, yeah.
5 over 6. No, I got that wrong. Never mind.
No. Pi over 3. The issue is that right? Yes or no? And the answer is no, it's not, because there's two answers. So this is minus a half because you missed the other answer. So the sine function is positive in the first and second quadrant. So we need a second quadrant answer as well. All right, so in the second quadrant, the angle is going to be pi minus the reference angle, which is going to be 2 pi over 3. So final answer, theta equals solution set pi over 3, comma, 2 pi over 3. There we go. All right, good enough? All right, let's move down to 51. 51 says express it in 4 significant digits. All right, well, we can do that. Number 51. Tangent of 3 pi over 5. Now, with a little bit of luck, my calculator is still in radians. Oh, yes, it is. Tangent 3 times pi divided by 5, close parentheses, 3 significant digits minus 3.078. 4 significant digits? Yes. Okay. That's 51. Oh, that went so smoothly. We'll try 54.
Why not? Why?
Huh? Who? What? Who? What'd I do? What? Who? Where? Minus 5. Didn't we just do this? Minus 5 pi over 6? Oh, yeah, but we're doing it differently. All right. The sine of the negative sine, 5 times pi divided by 6, close parentheses, minus a half. Oh, minus a half is wrong. Wrong, wrong. They want it to 4 significant digits. Silly me. Minus 0.5, 1, 2, 3. There we go. That's the correct answer. Minus a half would obviously be wrong. Yeah. Well, it'd only be wrong on Ben's paper. The rest of you guys are probably marked it right. And just to make it even, you know, and fair or whatever. What? All right. So we'll do 60. No, we won't. We'll do 58. Oh, 58 looks like a pain. 58. All right, so I got the sine of theta is minus 0.6825, and I want theta in radians from 0 to 2 pi again. Okay, my calculator is still in radians, so I'm going to take the arc sine of minus 0.6825, and I'm going to get that theta is minus 0.7512. Do I want, 4 significant digits. And this doesn't look much like a negative sign there, so we'll have to try that over again. Okay, now that's one answer, but there are 2 answers. I got to go find the other one. So I look at this, and my sine function does that. So that means I'm going to have 2 answers. I'm going to have a 4th quadrant answer, and I'm going to have a 3rd quadrant answer. And I probably want it to be in positive radians to boot, probably. I'm going to change this to 2 times pi minus the answer. I was using the negative key that time in case anybody was wondering. So this is 7.034 radians. Okay, so that's my fourth quadrant answer. My reference angle, that was a good way to spell reference, 0.7512. And in the third quadrant, which is my other answer, my angle is going to be pi plus the reference angle. Okay, so pi plus 0.7512, 3.893. So for my final answer, theta is, and I'd put them in alphabetical order, 3.893 and 7.034. And then I'd ask myself, what is my feeling about how accurate that is? Okay, so I would go back and say, what problem are we working anyway? I forget. 61. No, not 61. 64. So we're working 64. 58. 58. Okay, so we're working 58. Okay, so that's 58. So I want the sine of 3.893. And I get minus 0.6827. Looks good to me. And I take the sine of 7.034 and I get 0.6822. Why is it not negative? What did I do wrong?
Breaks down radians.
Yeah. This should be 2 times
I got negative 60.
pi.
26.
You did?
Mm-hmm.
Minus 0.7521. This is supposed to be a 5.532. The sine of 5.532, that's right. Okay, so this guy here, 5.532, not the other guy. When you put the 7.034 guy in, you didn't get a negative number out.
Oh no.
And that's the issue. 5.532. So I checked my work, I got it right. All right, now we're going to do 62 before we have to give up the room, or do we? I don't know. We do? Okay, 62. Well, Eric's not here yet, so there's no reason for you to rush, right? Not like you're going anywhere. 0.176. 176. Okay, so I'm going to take the arc sine. I'm going to make sure I'm still in radians. Arc sine 0.1876. And I come up with theta is 0.1887. Okay, and I'm going to recognize that as a first quadrant answer. And I'm going to recognize my sine function is positive in the first and second quadrant, so I'm going to want a second quadrant answer. So my second quadrant answer is going to be pi minus 0.1887. 0.87 because I recognize the first quadrant answer as my reference angle. Pi minus the answer, 2.953. All right, so my final answer is theta equals, in alphabetical order, 0.1876 and 2.953. And then I go back and I check my work, because last time I worked a problem like this just minutes ago, I got it wrong. 0.1887. Why can't I have an 887 here? 876. Why can't I have 887? I don't understand. 887. This comes up with something else you're going to have to know when I get around to telling you. The sine of 0.1887. Boom. 0.1875. Very good. I got it. And the sine of 2.953. Boom. Same answer. Boom. Oh, excellent. Now, when you're in your physics class, you're going to have problems, and the sine of theta is going to be approximately theta when theta is small. When theta is small. So in physics, sometimes we'll substitute sine of theta and just use a theta in radians. And we look at this and we say, well, the sine of theta is 0.876. Well, the theta is 0.1887. That's pretty close. So to a first approximation, that's the case. And if you look at the sine function close to 0, it almost has a slope of 1 there. Slope is equal to 1. And that's why the angle and the sine of the angle are very close to the same guy. All right, I knew you wanted to know that. All right, thank you very much.